For this problem, we want to figure out what are the optimal prices for advanced tickets and last-minute tickets. But before we can jump into the pricing problem, we need to think about how does the demand respond to prices? That is, we need to come up with a model for how does the demand respond to prices. Let's think about one of these two cases. Let's think about advanced demand, for example. And let's say we're given a bunch of prices, P1, P2, up to Pn, and the demand level based on our data, D1, D2, up to Dn. Now let's plot these. I'm going to put in a plot here. On the x-axis we have prices. On the y-axis we have demand. And here we have prices. I'm going to put P1, P2, up to Pn. And on the y-axis I have the demand, so D1, D2, up to Dn down here. And I have a bunch of points in my data. So when you're given data like this, how do you figure out how does demand respond to prices? As you've learned in a statistics class, the standard answer to this is you do a linear regression. What is a linear regression? You try to understand what is the line of best fit to the data. So let's say this here is the line of best fit to the data. What would make this the line of best fit? What would make this the line of best fit is that this line has a prediction on how demand responds to prices, and here are the prediction. This is the prediction for how demand responds to price 1, price 2, and so on. And there are errors here that you can measure between your prediction and your data. So here's your error 1, error 2, error 3. And the problem of linear regression is to find the line that minimizes the sum of these errors squared from 1 to n. Why squared? You do it squared for one reason, which is you want all the errors to be positive because you don't want positive errors to cancel out negative errors. But there are actually other options that you could use as well. There's another kind of regression that is minimizing the sum of absolute value of errors. This is called L1 regression. It's also correct, but it's less common than least squares regression. And we're going to stick here with least squares regression, which is the most classical one, which is the first one I mentioned. So how do I formulate a least squares regression as an optimization problem? The way you do it is you write decision variables. They're going to be A and B, where A is the intercept and B is the slope. And why an intercept and a slope? Because we're trying to find a line, right? And an intercept and a slope define a line. This means that our model here is that the demand responds to prices in the following way. It responds as A plus B times price. And our objective is going to be to minimize the sum of the errors from 1 to n, where n are the data points. And how do I calculate the errors? It's the value in my data minus the value in my prediction, right? And the value of my prediction is A plus B times Pi. So this is where the decision variables come in. And I need to square this to make this a least squares regression. And that's the problem. There are no constraints here. So you can interpret a linear regression as a nonlinear optimization problem where your goal is to minimize the sum of the squared errors.